Chapter 17, we learned about a diffraction grating. And this is a diffraction grating, and it has 1,000 lines per millimeter. And if I take this diffraction grating and put it in front of this white light bulb, you can see rainbows. And what it does is it breaks the light up into a spectrum, and you can see a spectrum of the light from this bulb on either side. Now we're going to take this diffraction grating and mount it on the camera, and then we're going to look at a single spectrum of this bulb out to the side. And now, with the diffraction grating on the camera, we see this. Here's the light source. Out here is a spectrum. The diffraction grating has bent the long wavelengths the most, and so the reds appear out on the far end of the spectrum. The blues are bent the least, so they appear on the close end of the spectrum. And what we have is a representation of the wavelengths of light, the colors of light that make up the light that comes off of this white light bulb. And this is an incandescent bulb. The filament glows because it's hot. And when you have something that glows because it's hot, you get this continuous spectrum. But, as we learn in chapter 29, if you look at the spectroscopy of elements, it's a very, very different story. This tube has mercury vapor inside it, and if I pass a current through it, I electrically excite the mercury atoms. They give off light, but if you look at the spectrum, you can see that we don't get every single color. This is a so-called line spectrum. And if you study the spectrum, you can tell that the spectrum is the spectrum of mercury, and I can tell what gas is inside this tube. In fact, some elements were discovered this way, most notably helium. If we look at the spectrum of helium gas, we get certain lines, and this spectrum was first observed in light that comes from the sun. And people looked at this, it was a spectrum of an element that wasn't known, and so it was named after the place it was discovered, Helios, the sun, and so that is where helium was discovered. But you can see the spectrum that we have here, we don't get all the colors, we only get certain possible wavelengths, and that has to do with the physics of atoms, and it has to do with an understanding of how we apply quantum mechanics to an atomic system. And the atomic system that we're most interested in is hydrogen. And the reason we start with hydrogen is it's the simplest atom. It's one proton and one electron. And here's a table of values for the energy levels of the electron in the field of a single proton. Basically, it's the energy levels of the electron in the hydrogen atom. And you can see there's certain possible quantized energy states. Now I have a question for you. Think back to what you learned about quantum jumps in chapter 28. If an electron makes a transition from state n equals 3 to state n equals 2, what is the energy of the photon that's emitted? We'll give you some choices. So if we look at the difference between the energy for state n equals 3 and state n equals 2, the difference is 1.89 electron volts. And that is the energy of the photon that's emitted. And so that transition corresponds to the red line in the hydrogen spectrum. Now, this is our introduction to the physics of how atoms work. But now we've been looking at light which is emitted. We can also look at light which is absorbed. And then, too, we can look at more complicated systems, not atoms, but molecules. And we'll do that in the next segment.